this subtopic is about amides. Okay, it's about amides. Amide we have done. Now amides. Okay, so just now amides is structures. Amides is RNH2, but amide is RCO NH something. Okay, so if here is hydrogens, then it will be primary. Okay? Primary amides. If here is hydrogens, so I mean this particular part. If this particular part is hydrogen, then it is primary amide. But if here is an alkyl group, then we call this secondary amides, because here already have R, then here has another R, so we call it secondary amides. Okay? So now let's see how to form amides. So we have primary amides here, RCOCl, acyl chloride, react with ammonia. So acyl chlorides form the Cl will always form HCl together with the H here. So they form HCl. And then the NH2 will act as the nucleophile. So the nucleophile will form a new bond with the CO here, with the carbon in fact. Okay? So they form RCONH2. This is primary amide. And the HCl may further react with the excess NH3. You know HCl is acid, NH3 is base. So they will further react to form ammonium chloride. Now we look at the secondary amide. RCOCl have to react with primary amide. Just now this is ammonia. Now this is primary amide. So for primary amide, first you need to know that the hydrogen, one of the hydrogen here will combine with the Cl here to form HCl. So then we have R prime and H that stick with the CO. As you can see, CO stick with the R prime and H. So they stick in that way. So bear in mind that the bond is formed between carbon and nitrogen, as I have drawn here. Carbon and nitrogen form a new bond. C and N form a new bond, and then this is called secondary amide because there are one R here and there is another R over there. So the reactions, no matter the first one or the second one, we call it nucleophilic substitution. Nucleophilic substitution. As you should be able to imagine, ammonia has lone pair, so it can form nucleophile. So the primary amide has lone pair also. So because of that, this one lone pair and this one has lone pair. Because of that, they can form or they can act as nucleophile. Reagent is concentrated ammonia for this case. Condition is room temperature and pressure. So example, ethanoic chloride, that is the acyl chloride. With 2 carbon, we call it ethanoic chloride. React with methylamine. Methylamine is the primary amide. So imagine that one of the H will combine with the Cl to form HCl, and then these nitrogens with lone pair will form a new covalent bond with this carbon. As you can see here, nitrogen, new covalent bond with the carbon. So this is secondary amide. Reason, because there are 2 alkyl group. The first alkyl group is here, the one that I circle. The second alkyl group is there. So we call it, how we name it, let's take a look. So this is secondary amide. So first of all, we look at this part. This part, the thing is, it shouldn't be methanamide, should be ethanamide. Should be ethanamide, this part, ethanamide. We don't want the M, ethanamide, because it has two carbon. So which two carbon that we talk about? This and this. So because of that, we call it ethanamide. Okay? Ethanamide. And this part we haven't talked about, N-methyl, the branch. So the methyl here stick with the nitrogen. So we call it N-methyl. Okay? N-methyl ethanamide. Okay. Now 11.8, neutrality of amides. So as comparisons, just now we already discussed, amide is basic, but here amide is neutral. It's neutral, so we have to know about this. Now let's see the reasons. As you can see here, the presence of the electron withdrawing oxygen atoms means that the lone pair on the amide's nitrogen's atom is not available to be donated to H plus ions. So there is a lone pair here, but this lone pair is not ready to form, to accept H plus, because the oxygen here will drag away the negative charge, make this lone pair not so negative. Okay? The oxygen here is electron withdrawing. So it drags the negative charge here. The lone pair is not so negative. So the H plus doesn't like to come and form a new covalent bond with the lone pair here. So because of that, it is not proton acceptor, and hence amides are neutral. Okay, are neutral. Okay, now let's see the reactions of amides. Hydrolysis of amides. So hydrolysis of amides is very similar to hydrolysis of ester. So you know, ester is where R, C, double bond O, and then O, R prime. This is ester, right? We break down over here, and then this part will form the carboxylic acid, RCOOH, and this part will form the alcohol, R prime OH. Yeah. So that is what happens to ester during hydrolysis. Now, amide works similarly. So amide, when you go through acidic hydrolysis, so this particular part break down, as you can see the arrow here, and after that, okay, let's see the equation. Our amide react with HCl in aqueous. This part break down. So hydrolysis means it involves the breakdown of H2O. So imagine H2O. I draw like this purposely. So hydrolysis, water breakdown, and the OH will come to stick with the C double bond O to form carboxylic acid, and the H will stick with the other side there. Okay? So which means HOH, okay, maybe I draw in the other way around, OH and H. Okay, so OH will come here, H will come here. So that's why they form these two products. So what kind of product is this? This is carboxylic acid, and this one is primary amine. And primary amine is basic. So if you react with the excess HCl, okay, excess HCl, not excess NH3, yeah, this is already basic. So we react with the excess HCl to form salt, R double prime and H3Cl. That is neutralization between primary amide with HCl. So that will form this. So we can do it under alkalines condition also, where you put NaOH. So the difference is the carboxylic acid that's supposed to form will be neutralized to form salt instead. So basically it is something like this. Imagine they form carboxylic acid, then they react with NaOH to form salt instead of carboxylic acid. Whereas the primary amines remains the same here, remain the same as the surrounding is alkaline. So this part is not neutralized. We remain as primary amines. Okay, so we have done, and okay, now amino acids. Okay, so this is the third compound. Okay, this chapter nitrogen compound we have amine, and amino acid. Okay, so three compounds, three types of compounds. Okay, so this one is NH2, RNH2. This is RCO, NH, and maybe R prime here. That is amide. Amino acid, what kind of structures does it take? So you can see this is the basic structures. We put the center as a carbon. So on the left of this carbon is NH2. On the right, carboxyl group, COOH. On top, hydrogen. At the bottom, side chain R. Can be alkyl group, can be hydrogen, can be others. Okay, so it depends on which amino acid we are talking about. Now, let's look at the optical activity. All amino acid except glycine. What is glycine? Glycine is where the R here is a hydrogen. So if the R here is hydrogen, then this carbon will have hydrogen up here and the hydrogen down here. That is for glycine. So because of that, glycine does not have chiral carbon, as this carbon stick to two hydrogens. Okay, glycine no optical activity. But other amino acid, yes. Other amino acid is where the R is something else, which is not hydrogen. Then they have a chiral carbon, and therefore they are optically active. Okay, so let's move on. 11.11 acid-base properties of amino acids. So as you can see, they are using glycine. They are using glycine as example here. As you can see, this carbon is stick to two hydrogen. That is glycine. Okay, so up here we have NH2. Down here we have COOH. So this is the basic group. This is the acidic group. Okay, so they will just do self-neutralizations where the acid part here neutralize the basic part here. So acid means donate H plus, and this one receive H plus, become this. This one donate H plus and become negatively charged. So that means our amino acid at the end, they can form an ions, which is called beta ion. Beta ion. So in what situation it happens? Let's take a look first. when they dissolve in water, as you can see here. When they dissolve in water, they form bitter ions. Now, let's see here. Basic amino group, yeah, and acidic carboxyl group interact. So that means this neutralize this, they interact in that way. Carboxyl group donates a proton. A proton means H plus to amino group. So this receives the H plus and become this. This donate the H plus and it become negatively charged. So amino group accepts protons and bitter ions form. So this is bitter ions. Emitter ions is the ion that contains regions of positive and negative charge. So positive charge is here, negative charge is here. Amino acid solids at room temperature and pressure due to ionic bonds that exist between bitter ions. So from here, you will realize that if water is present, there are bitter ions. If water is not present, there are solids form, there are still bitter ions. So in this case, you will see that, oh, bitter ions present in all situations. So yes, okay, in all situations. So in RTP, in solid form, bitter ion. When water is present, so it is still bitter ions.